In this video, let's pull together everything that we've learned so far to investigate the behavior of this function and hopefully graph the function. Okay, so we're going to use ideas like relative min and maxes, the concavity, first, second derivative, use all of that together to investigate the function. So first of all, let me just tell you, I have already done this, and it took me a couple times to really get this down so that this video didn't go on and on forever. So I'm going to make it look easy. It takes some time. I mean, I have several pages that look like this. Here's one. Here's another one. So I've been working on this, okay? And so these are not easy, but yet the stuff you're learning here is really important as far as using the mathematics to investigate the function. So first of all, I found out that it's going to be a lot easier if I just distribute the x to the 2/3 over as opposed to using the product rule. So we're going to start by doing that. So we got 5/2 x to the 2/3 minus, and this is like 3/3 and we're adding exponents, so that would be x to the 5/3. And now what I'm going to do is I'm going to take the first derivative of this function here, and so I'm going to bring down that 2/3, and the 2's cancel out. That leaves me with 5/3 x, subtracting 1 from the exponent, negative 1/3. Minus, I'm going to bring down the 5/3, subtract 1 from this exponent, so that'd be 3/3, so this would be 2/3. Okay, and so now let me go ahead and take the second derivative as well. Just get these two out of the way. So in this case, I'm going to take the second derivative of this, so I'm going to bring down that negative 1/3, and I'll get negative 5/9 x to the, and then subtract 3, so that would be 3/3, so that would be negative 4/3, minus, and then I'm going to bring the 2/3 down, and that would be 10/9 x, and then subtract 3/3, so this is negative 1/3. So that's the second derivative. Okay, so like I said, I've done this several times, and so I'm doing it in a certain way that's probably going to speed things up here. As you do these, you're going to have to investigate, use some scratch paper, and everything else. So what I'm going to do is I'm going to need to solve these equations, and of course these look very weird. Let me write it out. Not equations that we're used to. So you might be wondering, how in the world do we solve this equation? And by the way, I just ran out of ink, and this one might be low, but I have a new pack of pens. I might have to open them up. Yes, I think this is low. I might as well open up my new pack of pens here. Look at that. Beautiful. Enough hopefully for the rest of the class. Okay, this is equal to 0. Okay, so I tried to solve this in several different ways. Like, I brought this down to the denominator, combined over common denominator, and I did all of that. And here's a much more efficient way. So we're going to factor here, and this is a weird factor, and you're going to have to think about how to do this. But the idea is I'm going to factor out the least exponent. So negative 1/3 is smaller than 2/3. So I'm going to factor out x to the negative 1/3. I can also bring out the 5/3. Okay, so that's just going to leave me 1 here. And believe it or not, this is going to leave me with x here. Okay, and you can see that if I distribute this over here, I would have 3/3 and add it to negative 1/3, that would give me the 2/3. So how would I know what this exponent is? Well, think about what I do to go from here to here is I add these two, right? So this plus this is this. So this minus this is that. So if I'm going to factor out the negative 1/3, then I'm going to subtract a negative 1/3 from 2/3, and that's going to give me 3/3. Okay, subtract and negative is add, so it'd be 2/3 plus 1/3, and so that'd give me just x there. Okay, and so this is just the most efficient way of solving this, because now we find out that okay, I got two factors. This actually is equal to this. So this would be like 5/3 1 over the cubed root of x, right? Times 1 minus x is equal to 0. So that's actually what this is. So putting a 0 in here doesn't give me a 0. It would make the function undefined at that point. But a critical point occurs where the function's 0 or when it's undefined. So that is a critical point of the function. Okay, and then this would be another critical point, x equals 1, when the function is equal to 0. So these are the two critical points of our function. Again, I made this seem very easy without much work, but like I said, I had pages of work of trying to solve these things. And I just found that's the most efficient way. Okay, so we are usually, when we set the derivative equal to 0, usually the strategy is to factor. And if you have these fractional exponents, and what you want to do is factor out the least exponent and then go from there. That's what seems to work. So these are the critical points of the function. And so now we have the second derivative. So what we can do here, notice first of all, if I put in 0 here, both of these are negative exponents. They're going to bring these down. So it's not even defined there. So it's inconclusive at 0, right? So this one's, for the second derivative test, this is inconclusive. I'm finding minimum and maximums. Inconclusive. Okay, now I can put in 1 here, and I've done that already. If I put in 1 here, f double prime of 1, and you could use a calculator, I guess. In this case, it's not too bad because both of these, when you put in 1, they both end up being 1 to any power is 1. So I'm just taking negative 5/9 minus negative 10/9, and you actually get a negative 1.67 is what I got. So I put it in the calculator. But the point here is it's negative, and so we got a relative max here. Negative means it's concave down, and if you're concave down at a critical point, you're a relative max. Okay? So this one is still inconclusive. So we're going to need to make a table for 0. We're going to have to do the first derivative test. Now I want to tell you something, because something I said in the previous video wasn't right, or at least I didn't stress the fact. And this threw me off when I was working on this. I was wondering why this didn't work. And so what I'm talking about here is when I make my table with my intervals, so this is for the critical point x is equal to 0. What I said is we only have to worry about these two. So this would be 0 to 1. We only have to worry about these two intervals because I'm only finding this. And that is true, but what I did, I think, in my previous one is I just said 0 to infinity instead of 0 to 1. And it's important here because I got to pick my test point out of this interval. So let me explain to you what happened. Oh, and I just discovered something else. I'll explain that in a minute. What happened was I just had this much on my table, and I had 0 to infinity here, and I picked 8 because 8 worked well with the cubed root, because the cubed root of 8 is 2. So I picked 8, but it was in this interval. And I was getting the wrong sign, and I didn't understand why I was getting that sign and I was looking at the graph. So I was cheating. I was looking at the graph, and I knew, so I was just very, very confused about that. So, point being, you got to make sure you have those intervals. Even if you don't include this, don't put infinity there. Okay, that 1 is still a critical point, and you need those intervals, and you got to pick out of this interval. Okay, but the other thing I found out is we know that this is a max, and if that's a max, then the derivative has to be increasing and then decreasing. So this has to be positive, that has to be negative. So doing the second derivative test here and knowing that that's a max actually helps me complete this table, so I don't have to put in test points here. Okay, but actually in the one that I did, I did put in test points for these two. I picked 1/8 here, 1/8 because it worked well with the cubed roots. Okay, so but technically I wouldn't need to. I just need to put in a test point here, and a good test point would be -1, because then this cubed root of -1 would be negative, so that would be -5/3, and then this would, the -1 squared would be +1, cubed root would be 1, and you would have a -5/3, and the thing is you would get a negative. This ends up being a negative. So what we find out is at this critical point you have a min. So you got a min, you got a max. Okay, so now what I'm going to do, because we're going to graph these, I'm actually going to state what the min is. So at 0, when I put in 0 into here, I get 0. I'm sorry, when I put 0 into here, this is going to be, if I put 0 into here, it's undefined, right, because of that. But what I'm wanting to do is, if 0 is a min of this function, I want to know what the minimum value is at that point. So if I put in 0 there, I get 5/2, and I can do 0 to the 2/3 because that's not a negative exponent. And so that's fine. I get 0. So this whole thing is 0. So 0, 0. So the function goes through 0, 0, and that's actually a relative min. And it's a relative min where it's not a smooth turn, it's a sharp, some sort of sharp turn, because the derivative is undefined at that point. And now if I put in 1 here, so this is just going to be 1, and then this is 5/2 minus 2/2, so I get 3/2, and that's a max. So I'm thinking about graphing my function, the behavior of my function. So these are relative min and max of the original function. So now I want to work on the second derivative and talk about the concavity of the function. Okay, so what I need to do is I need to solve this derivative for 0. Okay, set that derivative equal to 0. And now what you might want to do is use the technique that I used over here to try to find the critical points of oh, by the way, let me think here. Yeah, so the yes, so not these would be this is the second derivative. This would be the critical points of the first derivative, right? Where the second derivative is equal to 0, that's when the inflection points occur, when it may change concavity, okay? So there's a lot to keep track of here. You'll have to go back and think about the different concepts and how they fit together. So, you may want to try to solve this. So the technique I used was factoring, and what I factored out was the smallest exponent, the least exponent. So go ahead, pause the video and see if you can solve this yourself. And then we'll start it back up again and we'll finish. Okay, so let's see how you did here. So to solve this, what I did is I took out a negative, and I could take out 5/9, a negative 5/9 here, because I can take it out here. So this would be a negative 5/9. And then the least exponent is the negative 4/3. That's smaller than the negative 1/3. Okay, so that leaves me just 1 here. And that's going to be a plus because I pulled out a negative 5/9. And then I get a 2 here. And then what I'm doing is I'm going to take negative 1/3 minus a negative 4/3. So that's negative 1/3 plus 4/3, which is just 3/3, which is just an exponent of 1, which is just x. So I get 1 plus 2x here. And so I have this equation. So now, here, remember the inflection points are going to be where the derivative is either, the second derivative is either undefined or 0. So the critical points of the first derivative. So it's going to be undefined here. This is a critical point, and then at x equals negative 1/2. It is undefined there as well. Okay? But we don't know if these are inflection points. So what we're going to need to do is we're going to need to make a table, and at this point I'm just going to do the full table as opposed to trying to take the derivative of this and doing a third derivative test to see if it's a maximum or minimum of the second derivative. So the idea here is forget what I just said. But the point here is I need to, in order to know if this is an inflection point, what I got to do is I got to see if the graph is changing its concavity. So I got to see if the sign of the second derivative changes at that point. So what I have here on my table, it would be a negative infinity to negative 1/2. And then I have negative 1/2 to 0. And then I have 0 to infinity. Okay, and this is what I did on my table here. I just picked negative 8, negative 1/8, and 8. And I suppose I could have picked negative 1 here. I picked negative, I had 8 in mind because you could take the cubed root of 8. And then, but this I had to get something between negative 1/2 and 0. So negative 1/8, and then this would be an 8. And so the second derivative, so I just plugged it in here with my calculator. With the 8 here, you could take the cubed root, and you could technically do it all by hand, but it would be a lot of work. So I just put these in my calculator. This ended up being like 0.52, so it was, the second derivative was positive here. And f double prime of negative 1/8 ended up being like approximately negative 6.67. So it was clearly negative. And then when I put in 8 here, f double prime of 8 ended up being negative 0.59. So and so that was a minus at 0. Okay, so this then was an inflection point. So and I'm going to put in negative 1/2, or let me just say, so the inflection point would be the point on the original graph. So you could put in negative 1/2 here and get that inflection point. So let me actually do that. I'm gonna do negative 1/2 to the 2/3, and then if this was negative 1/2 here, this would be plus 1/2. So this is 2.5 plus 1/2. That would be 3. And so this is like 1.89, and I think I can make a fraction out of that. Nope, I can't. Negative 1.89 approximately. So almost 2 there. So this is an inflection point. So in other words, the graph is the graph of the original function is changing its concavity here. It's going from being concave up to concave down, okay? And then here, this is not an inflection point. So x equals 0, which would be like 0, 0. This is not an inflection point. Okay, so we got ideas of its concavity. We got like minimum, maximum values. Let's just do a few more things. Y-intercepts. So the y-intercept is just where you put in 0 for x. So if I put in 0 for x here, I'm going to get 0. That's also a min. So the y-intercept is actually the min value. And it's also not differentiable at that point. So what about x-intercepts? This is where the graph is going to cross the x-axis. Well, technically at 0 it crosses the x-axis, right? This thing is it's when the function is equal to 0, is when the x values that make the function equal to 0. So 0, 0 is also the x-intercept. And then you have another one here at 5/2, okay? Because if I put in 5/2 here, this factor becomes 0, and the product will be 0. So that's another one. Okay, so I have a whole bunch of stuff, and there's no asymptotes on here. There's no place where, there's actually no place where this is undefined. So no, just one place where it's not differentiable. But this is actually continuous at every point, because this is continuous, and this is continuous, and so product of two continuous functions is continuous. All that stuff from an earlier chapter, right? So, but there's no asymptotes. Okay, so we have a bunch of stuff about this. Let's see if we can put it all together and make a graph and then see. Now I have to admit I did cheat. So if you do these and you need to look to help you along, that's fine. But use it in connection with the math and try to find the math and get the math to fit the graph, okay? And if you can actually do the math and then do the graph and be correct, that's really awesome, okay? So we'll make a big graph here. We'll say 1, 2, 3, 4. Of course, I experimented with this, and I knew kind of what we would need here. So okay, so we know that it goes through 0, 0, right? And it also passes through 5/2. So this is another point. These are x-intercepts. Now it's not going to just go through here because we know that this is a relative min. Okay? And we know that 1 is a relative max, and the max occurs at 1 3/2. Okay, so so it looks like it's going to have to at least come up and hit this, and then go back down here. Okay, and it's what you could do is you could plug in some points over here if you wanted to know where the points are. So let me actually do that. If I put in a -1 here, this would be negative. Nope, it wouldn't. It would just be 1. You'd get a negative. You'd take -1. The cubed root of -1 is -1 squared is just 1. And then -1 here, you would have 5/2 plus 2/2. So it'd be like 7/2, which is like 3.5. So like at -1, it would be 1, 2, 3.5. So we know it passes through that point. Okay. Now what about concave? So this is a min. So it looks like it's going to have to come, and it doesn't have any more intercepts. So it doesn't. I don't know if it's going to, it won't come down here. But it's non-differentiable there, so it looks like it's going to have to make a sharp, like this is some sort of sharp turn, right? And then it's going to go up and then back down is what it looks like. So let's look at some of these other things then. So we know that it's decreasing this whole time. But here's an interesting thing, that it has an inflection point at 1/2. So it's like -1/2. I'm sorry, it has an inflection point at -1/2, 1.89. So there's like here at -1/2, 1.89. There's like an inflection point here. And here it's concave up. So this graph is going to be like concave up, and then it changes to concave down. Okay? And so that's really weird. But it does that, and then here, this is not an inflection point. It's concave down, and then it'll be concave down here. So this is like concave down, and this is concave down, and it's concave down the entire time. And it goes through this point. And then you could like pick a point like 3 and see where it's at that point and kind of draw it. But this is something I don't think you would have noticed on the graph, that, and it has to go through this. But as you go on and on, this graph is actually concave up, and then it changes its concavity to this. But it's not very noticeable on the graph. Okay? So I have like -4 to 4, -4 to 4. So let's graph it from -4 to 4 either way and see how we did. So, yeah. Let's see what we did. See what it looks like. Oh, by the way, it's passing through that point, but this is where it changes its concavity down here. Okay, let's see. So there's the function. There's a graph of its derivative, but we're just going to graph the function here. And I'm going to do the window -4 to 4 and -4 to 4. Oh, there it comes. And so here, this is such an interesting thing, because here, at this point, it's changing its concavity at -1/2. So let me actually do second calc value, and I'll put in -1/2. So it's actually changing its concavity there. That is really weird. So let's see if we can get a window where maybe we could see that it is changing its concavity. So maybe something really wide. So maybe 1 to 3, and then, well, you can't stretch that. Well, let me just, what I'm going to do is I'm going to make a box around that. It's hard to know what to do. So I'm going to do the zoom box. I don't know if this will help or not. It's just really hard to see. You can almost just see it, but it's really hard. And you would never have noticed that. So here's a case where the calculus is helping you see things on the graph that you wouldn't notice normally. Yeah, that doesn't help, does it? And let's see if I even have 1/2 in there. I probably do. So I'm going to go to second calc value, negative 0.5. Yeah, right here, it's changing its concavity there. Okay, so maybe what we can do is we can change the window. I'm going to just see if I do, what if I do negative 100 to 100, and I do, I'm just curious, negative, let's do 0 to negative, or to 50. Okay, Zachariah, you need to be quiet. And let's see if this helps us at all. Yeah, you don't see it. Okay, so the point being, there is a concavity change there, but you would never have noticed it on the graph. So there you go. That's pulling all of this together. And I was going to do 2 other examples, but it's already pretty late in the day. So let me show you the ones I was going to do, and maybe at another point I can put them up. Where are they? You know what? I'm not seeing them, so I'm not sure where they are. So there you go. I think we'll just stop there because this video has already gone on for a half hour.